Welcome back to All This Math, where we make math simple. This is Professor Parker, and today we're going to get into some trigonometry. Now, if you haven't already, please go ahead and tap that subscribe button, subscribe to the channel, also hit the notifications button so you'll be notified whenever we put out new content on the channel. All right. Now, this right here behind me is one of my favorite type of problems to do, right? So you might see this in a trigonometry class. You might see this in a pre-calculus class. You may see this in a, whether you're on a high school level or the college level. You may see this type of problem where we have to solve an equation, but it's a trigonometric equation. All right, it's a trigonometric equation where we want to find the value of an angle. This symbol right here, theta, as in delta sigma theta, right? That represents an angle, the measurement of an angle. All right. So we're going to deal with the angle in terms of radians, not degrees, but in radians, right? And I'm going to show you how to solve this and how to solve an equation like this. So we first look at the instructions, solve for theta in this area. So this represents the unit circle, something called the unit circle. So the unit circle is basically like, if you think of the coordinate plane from algebra, the coordinate plane with the x-axis and the y-axis. So take that into consideration, right? Like this, you got your y-axis, you got your x-axis, but then there's like a circle that goes around it. And within the circle, it's like a bunch of, different angles. So this might be a 30-degree angle between the x-axis and this line right here. And then this might be a 45-degree angle between the x-axis and that line right there. And then you got the 60-degree angle between the x-axis and that line right there. And then this up here is a 90-degree angle. And it goes around counterclockwise, all the way until you get back here, which is 0 degrees, but also 360 degrees, because a complete circle is 360 degrees. And then you start over again. You know what I mean? All right. So what we're looking for is the angle, which can be seen within this unit circle, right? Between 0 and 2 pi. So 2 pi in radians is the same thing as 360. All right, so I'm going to just put 2 pi right here. Matter of fact, I'm going to draw the radian measurements or the radian equivalents of these 4 angles also. So 30 is pi over 6. 45 is pi over 4. 60 is pi over 3. It's a little sloppy. 90 is pi over 2. All right. And it goes on and on and on. Now, I think I have another video on the channel. If I don't, I need to upload one where I show you how to do the conversion from degree measurements to radian measurements and back, from radian measurements to degree measurements. All you really do is you just take whatever the degree measurement is and multiply it by a fraction, pi over 180. But we'll talk about that another time. All right. So now let's get back into this. So basically, when you approach this, we have sine of 2 theta is equal to 1/2. I'm trying to solve for theta. So whenever you're trying to solve an equation, you want to think about, well, how can I get that variable or that value isolated all by itself on one side of the equation? So theta is on the left side of the equation, right? So there are 2 things I need to get rid of. I need to get rid of this 2, and I need to get rid of this sine function, right? Think of sine as a function in and of itself, all right? So I need to get rid of it. And I'm going to get rid of the sine function first before I get rid of the 2 because I want to isolate the theta by itself, all right? So this is what I'm going to do. In order to get rid of the sine function, I have to use something called the inverse sine function. All right, the inverse sine function. And what does that look like? That looks like this. When I do that, I write inverse sine with this little -1 up here. That represents the inverse sine, right? On the left side, and also the inverse sine on the right side, right? Now, I just left the blank parentheses because I'm going to put this in there, and I'm going to put this in there. So let's see what that looks like. So I'm going to have inverse sine of the sine of 2 theta, and I'm going to have the inverse sine of 1/2, right? Now, the inverse sine of sine, they cancel each other out, right? They cancel each other out. Boom, boom. So that leaves me with just 2 theta. And then over here, the inverse sine of 1/2. Now, this is where we got to think about the unit circle. Now, if you're studying trigonometry and you're in a pre-calculus class and you're looking at this video because you're a little confused about some things that your teacher or your professor presented to you in class, you probably should have some familiarity with the unit circle and also the sine, cosine, and tangent values of some of the more basic angles that are used on a regular basis. For example, and if you are, then you'd be able to know, or at least have a reference, have like a printout of a unit circle, right, that you can refer back to, even if you don't have the values memorized. It's cool if you don't have it memorized, but at least have a reference that you can go to and look at to find out, in this case, what angle has a sine of 1/2. We need to be able to know what angle has a sine of 1/2. Now, I just happen to know that the angle that has a sine value of 1/2 is pi over 6, or 30 degrees, right, in the first quadrant. Now, there's also something else called all students take calculus. It's a mnemonic device, right? Similar to PEMDAS, right? You know, please excuse my dear African sister, you know what I mean? Parentheses, exponents, multiplication, division, addition, subtraction. Keep in mind, sometimes you divide before you multiply, though. Keep that in mind, though, right? But all students take calculus means that in the first quadrant, all of your trig ratios are going to be positive, or your trig values are going to be positive, sine, cosine, and tangent. In the second quadrant, the S stands for sine. Only sine is positive in the second quadrant. In the third quadrant, only tangent is positive. In the fourth quadrant, only cosine is positive. So I'm looking for the angle that has a positive value of 1/2 for its sine value. So that's two different angles. That's pi over 6, and that's also the reflection of that angle, which is 5 pi over 6. Now, again, how do I know that? I just happen to know that because I have familiarity with the unit circle. If you're unfamiliar with the unit circle, then go into the internet, go into your textbook, and get a copy of the unit circle and just study it and focus on it and understand the values of the different angles and their sine, cosine, and tangent values. Actually, if you memorize the sine values, you can kind of figure out, if you understand cofunctions, you can kind of figure out what the cosine values are. And then once you know the sine and cosine values, you can figure out the tangent values, right? But at any rate, we know that the two angles that have a positive sine value of 1/2 are pi over 6 and 5 pi over 6. So what I'm going to do is I'm going to say 2 theta is equal to pi over 6, and it's also equal to 5 pi over 6, right? Now, we got to be careful, though, right? And this is something that I forgot, recently when I was trying to go over some problems like this, right? I had to remind myself, check my notes, and look into this more deeply, because some people would just stop here and then they would get rid of this 2 and think, oh, okay, I'm done. But no, you won't be done, because actually what you got to do is, let me rewrite this. So I'm going to rewrite this in 2 ways because I got 2 different answers, right? So I'm going to rewrite it as 2 theta is equal to pi over 6 plus 2 pi times n. You got to remember that. That part right there, that plus 2 pi n, is very important. It's very important. All right. Now, also, I'm going to have 2 theta is equal to 5 pi over 6 plus 2 pi n. Now, what this plus 2 pi n part means is basically is that because it's a circle, right, we can go beyond just the first quadrant. We can go around the circle more than once, right? And we want to go around the circle as many times as we can, because this is a double angle, right? Because it's 2 times theta, as long as our value is less than 2 pi, right? And you'll see what happens. So watch what happens. In order to solve for theta, I need to get rid of this 2. In order to get rid of the 2, I got to divide by 2. I can divide by 2, or I can multiply by 1/2. Multiplying by 1/2 or dividing by 2 are really the same thing. All right. So I'm going to just multiply by 1/2 because it makes the math easier. Because I don't want to have to divide a fraction by another fraction, because then things get a little crazy looking. I mean, it's easy to do, but it get a little crazy looking. So, and I'm going to multiply by 1/2 over here. So these 2's cancel out, leaving me with theta is equal to pi over 6 times 1/2 is pi over 12. Because 1 times pi is pi, 6 times 2 is 12. And then over here, we got 2 pi n over 2. These 2's are going to cancel out, leaving me with just pi n, right? So that's one of my answers, right? This is the general formula of the answer. Pi over 12 plus pi n. Over here, I'm going to do the same thing. I got to multiply by 1/2. I know it's a little crowded, but understand that these are two separate equations, basically. And then over here, we got times 1/2. These twos cancel out. I got theta equals 5 pi over 12 plus pi n, right? So these are my two general equations of the general equation of my solutions, or my general formula of my solutions. Pi over 12 plus pi n, right? So if n was, now n is going to be an integer, right? That indicates how many times we're going to go around the circle, okay? Or move through the circle. So if n was 0, it would just be pi over 12 plus 0, because pi times 0 is just 0. So pi over 12 is one of my answers, all right? But what if n was 1? If n was 1, then it would be pi over 12 plus pi, because pi times 1 is just pi. Now, you got to know something about adding and subtracting fractions. You got to remember from way back how we added and subtracted fractions, how we found LCDs and whatnot. So this is the same thing as saying pi over 12 plus 12 pi over 12. Because in order to get my LCD to be 12, the numerator is going to have to change to a 12 pi. So now I can basically combine like terms in my numerator. 1 pi plus 12 pi is 13 pi. So now I got 13 pi over 12. So that's another one of my answers. So pi over 12 is one of my answers, and 13 pi over 12 is one of my answers. Now let me try to break this down a little bit as to why this makes sense. Notice how we said that all the values of theta must be greater than 0, but less than 2 pi, right? So 2 pi is going to be 360. It's going to be right here. Now I wonder, think about this. Where's 13 pi over 12? Think about 13/12 as a fraction. It's an improper fraction. But if it was a mixed number, it would be 1 and 1/12. 1 and 1/12 is less than 2 of something, right? This is 2 pi. So how many pi's? 2 pi's. How many pi's right here? 1 and 1/12 of a pi, right? So this is still in this range. So this is why this part right here is critical. This plus 2 pi n part is critical. Because if I didn't include this part, then I wouldn't have thought to do this math right here, and I wouldn't have got this as one of my answers, and then my solution set would be incomplete, right? Now, we're still not done yet, because I still got to carry it over here like that with the 5 pi over 12. I still got to do my thing over here with that. But I just want you to understand, that's why we got to change these n values. See, the n value at first is 0, which leaves us with pi over 12. And then when you make n 1, it's going to give us 13 pi over 12. Now, check this out, though. How do you know when to stop, right? You know when to stop because we're in this range. We don't want to go past 2 pi, right? We don't want an angle that's past 2 pi. We're in this range. If I go to n equals 2, that's going to give me 24 pi over 12, right? And what's 24 plus 1 pi? 24 pi plus 1 pi is 25 pi's. Now, 25 over 12 is more than 2. 25 over 12 is more than 2, right? Because as a mixed number, that's going to be 2 and 1/12. Now, 2 and 1/12 is more than 2. So therefore, I can stop at n equals 1, right? So I'm going to use n equals 0 and n equals 1, right? Now I'm going to slide over here and do the same thing. Now, if n equals 0, that's just 5 pi over 12. That's another one of my answers. And when n is 1, it's going to be 5 pi over 12 plus just pi, right? But I got to give myself a common denominator. So I need to have 5 pi over 12 plus 12 pi over 12, right? And then that's going to give me 17 pi over 12. Right? Which is also in this range. It's in this range because I need to be less than 2 pi, right? 17/12, if I flip that into a mixed number, that's going to be 1 and 5/12. 1 and 5/12 is less than 2. So I'm cool. I'm cool with this, right? So boom, that's another solution. Boom, that's another solution. And this pi over 12 that I had in the first place, these are my 4 solutions. Pi over 12, 13 pi over 12, 5 pi over 12, and 17 pi over 12. Now, if you're wondering where those angles are, that is in, let me see. 5 pi over 6 is right here. Well, that wasn't even the solution, though. These aren't even really the solutions. These are actually just, those were the angles. Pi over 6 and 5 pi over 6 are the angles that have an inverse sine of 1/2, right? But I'm going to leave that there. I'm going to stop right there for now because this video is getting kind of long. But I just want to show you like the process of how to solve trigonometric equations, right? Trigonometric equations. And basically, we just take what we already know from solving algebraic equations and we just apply it and just add some information that we know from trigonometry about the unit circle and just add that into the mix. You know what I'm saying? That's really all we do. So again, if you have not subscribed, subscribe to the channel, turn on the post notifications, share some of these videos, tell other people about what we're doing over here, all this math, where we're trying to make math simple and accessible to everybody. All right. And as always, remember, there's all this math all around you. Peace.